Okay, welcome everybody to lecture number 9 on convex analysis. Today's topic will be subgradients. You may have heard of subgradients before, but anyway, we're going to treat them here in the lecture today at length. And there's two starter questions for the topic of last lecture on the Moreau envelope. But apparently there are no answers yet, so let's wait until we see something over there. Okay, so then let's just jump in. Okay, so subgradients, section 9 on subgradients. So, and we've seen that convex functions have some inbuilt continuity. So if a convex function is locally Lipschitz in case it's locally bounded. So if it's really not jumping up to plus infinity at some point, then away from that point it is locally Lipschitz continuous. So that's already great, but there's more. And there's even more than we will show here. What we show today is that the convex functions also have some kind of inbuilt differentiability in some sense. Okay, so when we start with the notion of directional derivative. So if you have a function which is defined on the plane, and you're sitting in some point x0 and you have a direction v, then you can consider the function f from that point away in this direction a little bit. So something like, let's just write it over here, f of x0 plus something, a little bit of v. And if you then have a look at how much the function value has changed between the point here and slightly in this direction over there, relative to the amount you scale the direction, and this gives you a kind of a change in this direction here. And if you now take the derivative, not the derivative, the limit, if h goes to 0, and since you now want to look in this direction and not in the opposite direction, we take it to it like this, which means that the value of the limit is that what we get if you take a sequence of positive hn's converging to 0 in a decreasing way. So for any sequence, the limit has to exist and has to be the same. So and this is exactly what is the directional derivative. Here it's denoted with a capital D of f at the point x0 and then in direction v. So this is the directional derivative. Of course, in case it exists. Okay. And I think one little bit more precise would be this the one-sided, because there's also the notion of directional derivative where you take the limit here for arbitrary h, so also from the other side. Okay. Okay, and then we need one definition. This is just because the directional derivative has a certain property, and we just define it here. So if you have a function f from Rd to the extended real numbers, we call this positively homogeneous. If f of lambda x is equal to lambda f of x for lambda positive. So we can pull positive scalars out, but not negative ones. If you can pull all lambdas out, but with the absolute value outside here, this would be called homogeneity. But this is only positive homogeneity. And so standard example is norms are positively homogeneous. Okay, but also linear functions, and so another function which is positively homogeneous but not linear, not a norm, would be a function which goes linear in this direction and linear in that direction. But it's a little bit more obvious, so with different slopes. So that's also a positively homogeneous function, right? So here it scales linear and there it scales linear. So it's kind of linear along the rays. Okay, so and now comes the theorem about directional derivatives of convex functions. So for general functions, directional derivative need really not exist, and if they exist, they probably don't have too many nice properties actually. But for convexity, everything is a little bit nicer. So f shall be convex, we take a point where f is finite and any direction in Rd, and then let's give this name here. The limit star above here always exists, not as a real number, but at least in the extended real number. So it may be any real number, or maybe plus or minus infinity. That may be possible. And it holds that this directional derivative is not only given by a limit, but also as an infimum, the infimum over all positive h, and then the same difference quotient here. So we can replace the limit of over decreasing h by the infimum over all positive h, and this will be true because this has a certain monotonicity property built in. So that's one thing. Moreover, we have that the directional derivative, if we view the direction as a variable, then it's convex and positively homogeneous. Okay, and there's more. So the directional derivative is convex in the direction, that's nice, positively homogeneous in the direction, and it holds that we have a simple upper bounds that's upper bounded by f of x plus v minus f of x 0. So if in case you need to estimate the directional derivative, that's a simple estimate you get for free just as a difference. And one more thing, if f is also not negative infinity at that point here, so if you look in the other direction, then you even have a lower bound for the directional derivative, which looks like the other difference. Okay, so that's the statements. In particular, that's one thing which is so in particular you have that this directional derivative is always finite whenever x0 is in the interior of the domain. So this last claim here follows from the two, because for the directional derivative you only need to consider v which are small, because you take the limit over h times v. So and if v is small, then x0 plus v and x0 minus v are also in the domain if x in the 0 comes from the interior of the domain. So this is a difference of two finite numbers. That's the difference of two finite numbers, and this is an upper and lower bound, so this is also a finite number. Okay, so that's it. That's we have about directional derivative, and so let's prove it. Okay. Yeah, and the most important thing is that we have a certain monotonicity here. Okay. So we want to show that the difference quotient f of x0 plus hv minus f of x0 over s is monotone and increasing in h. So this is what we want to show, because if you have that, then this is clear, because this is then decreasing if h decreases, and then the limit is the infimum, and also this then follows from that, because h equals, taking h equals 1 here is of course an upper bound for the infimum, and then you also have that. So this monotonicity property of the difference quotient tells us basically everything what we need. Okay, so consider the h's, h1 and h2, h2 being the larger one, and then use convexity in an appropriate way. So what we do is we write down that guy here with h1, and transform this here into a convex combination in a slightly non-obvious way. So what we need is we would like to have h2 times v over here. So we would like to have x0 plus h2 times v, so what we're going to multiply Oh, there's more typos here, I guess. Yeah. Oops. We pre-multiply by h1 divided by h2. To make up for that, what we need to add is 1 minus h1 over h2, so because we have a convex combination, and if we just add x0 over here, then everything is as it has been before. So we have these x0, these coefficients add up to 1, so this gives the full x0, and h1 over h2 times v is h1 times v as before. Okay. That's it. So now convexity. Convexity gives h1 over h2 f of x0 plus h2 times v plus 1 minus h1 over h2 f of x0 minus f of x0. Okay, and then we're almost there. We just observe that this one here cancels with that minus 1 over there, and then we can just pull out the factor h1 over h2 of f of x0 plus h2 times v minus f of h0, and then we have it. Just divide by h1. Dividing by h1 gives on the left hand side this difference quotient with h1, on the right hand side the difference quotient with h2. Okay, so this what follows, the map h maps to f of x0 plus h times v minus f of x0 divided by h is increasing in h. So by increasing I mean increasing meaning not strictly increasing, so it can be constant, of course. If f is constant, then it's constant. Or if f is linear, it's also constant. Okay, so I use the word increasing and strictly increasing, and other people would use increasing for strictly increasing and non-decreasing for increasing, which is of course correct, but I find it a bit weird because it always takes me half a second to figure out that non-decreasing is actually increasing. Okay, but anyway. Okay, so from this, so this shows this here. Let's do 2 stars over here. So from this, 2 stars, and h equals 1 shows 3 stars. And now comes the lower bound. So this is the 3 stars inequality, also follows by h equals 1 from 2 stars. And now the lower inequality we take a v such that f of x0 minus v is not minus infinity. And then we have 2 cases. First case is if f of x0 minus v is actually plus infinity, or we have df of x0 v is equal plus infinity, then this inequality is always fulfilled, because in this case we have infinity over here, in this case we have minus infinity over there. Everything is fine. Okay, so if else, so otherwise, both are finite. And then we have infinity is larger or equal to d of the directional derivative into direction v, which is now the limit of f of h0 plus, oops, there's another typo. H times v minus f of x0 divided by h. And what we now see is there exists an h bar, a positive one, such that this differential is finite. Finite whenever h is smaller than h bar. this included whatever. Because otherwise this limit could not be infinite, would be infinite if this would not exist. Okay, what do we have from this? From this we know that this difference quotient here is finite, and hence in total we have that this guy and also this guy are in the domain. So we are finite at this point, this by assumption, and this follows from here because, because this has to be a finite number. And hence for h smaller h bar and still positive, we can do the following. We can write f of x0 as a convex combination, as slightly non-obvious, but it's x0 plus hv plus h over 1 plus h x0 minus v. Let's check again that this is again actually true. So of course it's a convex combination, and these add up to 1. So these guys added together gives the x0, and this is h over 1 plus hv, and this is negative h over 1 plus hv. So this is actually x0 here. Okay, convexity again, it's 1 over 1 plus h f of x0 plus hv plus h over 1 plus h f of x0 minus v. And this now we rearrange to f of x0 minus f of x0 minus v. And so what do we get when we do that? This is bounded from above by f of x0 plus h times v minus f of x0 divided by h. A little bit, it takes a little time to check that. Probably take to multiply maybe by 1 plus h, bring one of the over the other side, this over here, divide by h, and you get this. Okay, and so then this 4-star thing here, if we let h go to 0, implies the 4-star thing. So because this is the upper bound. Oops. That's an upper bound for this. So this is an upper bound for all h, and h to 0 turns this into the directional derivative, and this is exactly the 4-star thing. Okay, good. So what else do we have? We still need to show that the directional derivative is convex and positively homogeneous. And there's one more thing to show. Okay, so next point, the directional derivative at x0 direction of the free variable is convex. Okay, so take two directions for which this is a finite number, and then we can do, we just plug in a convex combination here, lambda v1 plus 1 minus lambda v2 minus f of x0, and expand everything out. So we basically, what you do is to write x0 as lambda x0 plus 1 minus lambda x0, rearrange the things to see that you get 2. So let us write it up. It's you can write it like f of lambda x0 plus h v1 plus 1 minus lambda x0 plus h v2, and then here you write it as lambda f of x0 minus 1 minus lambda f of x0. Using convexity here and rearranging gives you lambda f of x1 plus h v1 minus f of x0 plus 1 minus lambda f of x0 plus h v2 minus f of x0. And so now you can divide by h, and letting h go to 0 shows the claim. Okay, that's that. And okay. Positively homogeneous. So this directional derivative of x0 positively homogeneous. So that's even simpler. You put an h times v in here, expand it as the limit d of x0. Not an h, I use h for this limit. Use lambda here probably. There's lambda hv. Oh. And this is of course an f minus f of x divided by h. H decreases to 0. And what we now do is we take h bar as lambda times h. So, and if h goes to 0, h bar also goes to 0. So that's the same limit of h bar down to 0. Of course, above here we have x0 plus h bar times v minus f of x0. And down here, if we substitute h bar is equals lambda h, h is h bar over lambda, so this is h bar, and all is multiplied by lambda. And so do you see that this is exactly lambda times the directional derivative of x0 in direction v. So it's a simple substitution. Okay, and finally, that this guy here, finite if x0 is in the interior of the domain of f. Okay, and yeah, we use the upper and lower bounds we have. So what we write down is that this guy here, x0 plus lambda v, if you do it like this is exactly by positive homogeneity the directional derivative itself. If you scale up by lambda here and scale down by lambda over there, it stays the same. But for this guy we have an upper bound, so we first copy the 1 over lambda, and for this guy we have this upper bound that it's f of x0 plus lambda v minus f of x0. So we use the upper bound with h equals 1, but now we have a lambda here, so this is a lambda over there. And lower bound is the same, 1 minus lambda, then it's the same but the opposite, f of x0 minus f of x0 minus lambda v. Okay, so and these guys are finite, so this is finite. So for lambda small enough, this is finite here. That's the point. This is because x is in the interior of the domain of f. So if lambda is small enough, this guy here is a finite number and this guy is a finite number. So also x0 is in the interior of the domain of f, and that was the proof. Okay, that's about directional derivative. So that's nice. They exist and everything's good. Okay, so that's better than for ordinary functions. But anyway, so the convexity is a strong thing. It's the strongest problem. So why is the convexity related to differentiability at all? It's because convex functions have kind of supporting hyperplanes. That's the important thing. And differentiability is not only it's not supporting hyperplanes but approximating hyperplanes. But supporting hyperplane has at least the property that the graph is totally on one side, so it cannot behave too weirdly in the region of the hyperplane. So it cannot stick through the hyperplane, and not locally, and not even globally. So the supporting hyperplanes, they are a little bit of like they also do some kind of approximation. So not in a way like differentiable. It happens for differentiable functions, but it still happens anyway. In a slightly different way. So what we already seen is that theorem 5.1 showed us that if f is differentiable and convex, you have that that for all x0 and x, you have that f of x is larger equal to f of x0 plus inner product the gradient of f of x0 x minus x0. So we already seen that. If it's differentiable and convex, you always have this. If it's only differentiable, you have an equality sign plus a small o of the difference of x minus x0. So this is the first order Taylor approximation. For differentiable functions, you know that the difference of function minus linearization is small. And for convex functions, you know that the function is above its linearization. Okay. So and then, if we adopt differentiability, the only thing which is bad about this definition here, about this property, is that this guy does not exist. So if we don't have differentiability, we can't guarantee that something like this exists at all. But good thing is, why should we need it to have this this gradient of f at all? We can just say, well, if some vector p fulfills this, or it has a property that the inequality is fulfilled for all x, then just call it a kind of gradient, and we do it, and this is what the subgradient is about. So we take this as a motivation for a more general definition. We define, not 5, it's 9, 3. If f from Rd to the extended numbers is convex, we have a point in the domain, and then we say then a vector p in Rd is a subgradient of f at x0 if, and then the condition is for all other points x in Rd, it should hold that f of x is larger or equal to f of x0 plus inner product p with x minus x0. Okay, so a subgradient is kind of a slope, something which can act as a slope, or can act as a slope as at a supporting hyperplane. You always see that if you plug in x equal x0 on both sides, which you should be able to do so, this guy is vanishing, and you always have that the left and right hand side coincide. So for x equals x0, they are the same, which means that this linear function here always touches the graph at the point x0. And so this gives you an affine hyperplane with a slope p, and this says that this hyperplane here should touch the graph at the point x0 and stay totally below the graph everywhere else. So in the obvious picture, which one always words, is something like you paint a convex function like this, which has a slight kink over here, and of course at a point like that here, where the function is kind of smooth, then the subgradient, there's only one subgradient, which is the slope of that supporting hyperplane, in this case an affine linear function in 1D. But here at that point you have different slopes available. So this will, of course, this slope here would give you a subgradient, that slope gives you a subgradient, and that slope gives you a subgradient. Actually all slopes between this negative slope here and this slope here give you a subgradient. And in this case you may even see that the set of subgradients at that point here is in fact a closed interval. This is the smallest number here corresponding to that slope, and this is the largest number in that. So by the way, I guess slope is the standard word for Steigung. German word Steigung. Okay, the definition is not over. There's more notation with this object here. Just a partial d, but with not just like that, is equal to the set of all subgradients at x0. So it's always a set. It may contain just one vector or number, and if d is equal to 1, but it also may contain more of them. So here you would write, if this holds, you would write p is an element of the subgradient of x0, of course. Okay, and this is this guy here is called the subdifferential of f x0. Okay. There's a little bit more to say. One thing is if x0 is not in the domain of f, meaning that this is not, it's infinite. So then we always say that the subdifferential at that point is actually the empty set. Because, well, you can't linearize something at infinity. It doesn't make any sense. So there's a constant infinity, and then one could say in principle that if f is constantly plus infinity, then every p would be a subgradient, but that doesn't make too much sense actually. So we just take this condition, this convention here, because the function plus infinity is not that interesting anyways. Moreover, we denote the domain of the subgradient. This is by definition the set of all x such that the subdifferential of x is not empty. And we also say that if x0 is in the domain of the subdifferential, we say that f is subdifferentiable at x0. So if the subgradient is actually non-zero. And probably we should think about, can that even happen? Is it possible that no subgradient exists? Yeah, it may happen. But how? Oh, and I see we're going pretty fast, but anyway, it's not too bad probably. Just end early, and you can pause while listening anyways. So may it be that a function is not subdifferentiable at some point? So is it possible that there's actually no affine hyperplane below? So let's consider a few examples. And the good thing about subgradient is in 1D you can always do it graphically. Nothing goes wrong. So with differentiability, I'm always a little bit, so there may be some slight quirks which is really difficult to see what's happening with the derivative. In the convex case is always what you can draw is always nice, at least in one dimension. Higher dimensions are more difficult to imagine, to visualize, but most intuitions you get from 1D are pretty nice. So first let's consider a few examples. Just graphically, yeah, let's just do it right now. So for example, if our function here is an indicator of something. So let's say here from A to B. So our f is equal to the indicator of, let's say, the closed interval. So that we have a convex and lower semi-continuous function. Indicator of the interval from A to B. So what do we have as slopes? So of course, so let's start writing down the subgradient or the subdifferential. So of course, if x is smaller than a or larger than b, so meaning we are outside the interval and the function is already plus infinity, we have by definition here subgradient empty. Okay. So what happens if x is in the interior of the domain of f? So it's strictly in the interior of the interval from a to b. So at a point like that, what is the slope of a affine hyperplane? We can put below. It has to touch here, but the function is locally constant, so the slope has to be 0. Here we go. Slope. I used to have a subgradient here, but can't find it right now. So that's all we can put, all the slopes we can put below the function at that point. But what is now at the point x equals, let's say, b on the right end of the interval? So and here we can put a lot of subgradients actually. For example, that one here, slope approximately 1, but you can also use slope approximately 2 or slope approximately 1/2. Slope equal to 0 also works. And we can make the slopes arbitrarily large. So any number larger than 0 gives you a slope below. So at that point here, the subgradient is actually the interval from 0 to infinity, and of course infinity open. Okay, and what is at x equals a? At x equals a, it's kind of the other way around. All the negative slopes work, and also slope 0 works as well. So here we have minus infinity to 0. So these are all the slopes. And so graphically, it would look like this. If here is A and here is our B, then the subgradient would kind of be like, here it's constant 0, constant 0, constant 0, and at that point it's this full line here extending to plus infinity. So that's kind of the graph of the subgradient map in this case. Okay, these shapes will be important in what comes. Okay. So we will see examples that subdifferentials may be empty at some point. So here at least, so at points of non-differentiability, subgradients tend to be larger, which is actually nice in the following. So points where convex functions are not differentiable do not cause any problems for subdifferentials or subgradients, but it's more or less the other way around. You have more subgradients at that point. Okay, the consequence of the definition is that the set of subgradients at a certain point is always convex and closed. Okay, that's also nice, and it's fairly simple to see, so there's nothing difficult behind it. So in this case, it's true. So how can you visualize that set? So you pick an x0 and look at this how this vertical planes intersects with this graph here, or you can just look at here. And actually, this was wrong. So at this point, I should have written like a set which contains 0. So, and of course, this is convex and closed, this is convex and closed, that's convex and closed. In all cases, that's true. Okay, so and to show it, let's first show closed. So if you have Pn in the subgradients, it means that for all x, you have f of x larger or equal to f of x0 plus Pn x minus x0. And if you now have that Pn converges to P, then by continuity of the inner product, this converges to P x0 minus x, and of course the rest stays the same. And so this holds for all x. In the limit, everything stays true, so this still holds for all x, and this shows that P is in the subgradient, and this shows closeness, sequentially closeness. For those of you who know about Hilbert spaces, everything is totally the same in Hilbert space here because we just need an inner product, nothing else. And you even see that this totally goes through in Hilbert space because the inner product is still continuous with respect to the convergence implied by the norm induced by the inner product. But there's even more, it even works for weak convergence. So if the Pn do weakly converge to P, the inner product still converges. That's basically the definition. So and the Hilbert spaces, the subdifferential is even weakly closed, weakly sequentially closed, to be precise. Okay, what about convex? Yeah, this is basically the same. If you have P and Q in the subgradient, you write down the subgradient inequalities. Yeah, so you can do it like this. X0, I use X and Y, but anyways, okay, let's write it as in the definition. So what you do now is you write down f of x as lambda f of x 0, 0 plus 1 minus lambda f of x0, and use subgradient for this and that separately. So for this you get it's largely equal than lambda f. Also, sorry, this should have been an x again. Actually, x was 2. Was what I wanted to write. X here, x here, x here. So now subgradient inequality for this guy shows is largely equal to f of x0 plus p x minus x0, and here which is larger or equal to f of x0 plus q x minus x0. And if you just do the algebra here, you see that this is f of x0 plus lambda p plus 1 minus lambda q x minus x0. And this holds for all x, so for all this inequality holds for all x, so this totally line of inequalities holds for all x, and this shows that lambda p plus 1 minus lambda q is again the subgradient of f of x0. Okay, good. Similar answer, so maybe somebody will chime in and give an answer, otherwise I will just leave it like that in the chat. Okay, so that was first half. In the next half we will have a closer look on the how the notion of subgradient interacts with the notion of directional differentiability, and also have a look at a few more examples. But now for the break, and the break again consists of some dead jokes. So see you in 2 minutes. Okay, here we go. Okay. So, one example, which I fit in this corner here. So we have one example over there, but there's one official example. It's f of x equals the absolute value of x. And again, it's simple to calculate the subgradient graphically. So that's f. And then you see that the subgradient f of x, so again, in different places it should be different. So for example, for positive x, if you're here, the function is differentiable, so there's only one plane which can kind of really support that function, and its slope is 1. Again, at x negative, the slope is -1, and there's only that slope, and the only point of interest is 0, and here you can fit all the slopes between +1 and -1 under the graph. So there it's actually the closed interval from -1 to 1 at x equals 0. So the graph of the subdifferential kind of looks like it stays -1, -1, then it has a full line and stays like this. That's the graph of the subdifferential. which looks kind of the opposite like this, and it's no coincidence, and we will see a deeper connection between these two functions later, probably only in the second half of the function, because we won't be able to treat duality of convex functions within this in the first half, unfortunately. Okay, so that was another example. Will be important in the following, the absolute value. Okay, so now for the interplay between directional derivatives and subgradients. Okay, so if you have a function from Rd to R, just convex, and f of x0 should be a real number, so it could also say it's in the domain, but let's say it like this, then it holds that the subdifferential at x0 is exactly equal to the set of all p in Rd, all vectors, such that for all directions it holds that, so in Rd, it holds that the inner product of this p with v is smaller or equal to the directional derivative at x0 in this direction. This kind of makes sense to me. So the subdifferential, so this gives a slope, so the magnitude of this number is a slope in the direction of v, scaled by the length of v, but anyway, so for directional derivative, I always, in my head, I always imagine that the v is normalized anyway, so as norm 1, because positive homogeneity, so this is valid. So this is just the slope in the direction of v, and it can be larger than the actual slope in this direction. But anything smaller would still stay below that. Okay, this gets a star because you're going to cite it in the proof. Okay, okay, let's denote this guy here by m, and then we do both inclusion. So let's start with this inclusion here, that subgradients p also fulfill this. So okay, that means we have to stay with the let p be in the subdifferentiable, and then we said we work with x equals x0 plus hv for some positive h. Okay. Okay, so by the definition of the differential or of the subgradient, and actually this I forgot to say that so this inequality is also called the subgradient inequality, which makes a lot of sense because it's the one defining the subgradient. So I will refer to this inequality as the subgradient inequality. So by the subgradient inequality, we have that f of x0 plus h times v is larger or equal to f of x0 plus p times this minus that. This minus that is h times v actually. Or put differently, we have f of x0 plus hv minus f of x0 is larger or equal phv. And now, okay, I could even just divide by h, and now h goes to 0. This holds for all positive h, so it also holds in the limit. In the limit, the left-hand side turns to this guy here. And this shows p is in m. Okay, that was that inclusion, and the other inclusion is also not so difficult. So let's see, let p be in m. And by our first theorem on the directional derivative, we know that for all v, it holds that the directional derivative of f of x0 to v is smaller or equal to f of x0 plus v minus f of x0. Okay, and so by this is a theorem 9.2, but by assumption we know p is in m that this is largely equal to p times v in the inner product. Okay, this holds for all v, and if you now set x2 is x0 plus v, then we know that from this that for all x we have that p in our product with, so what is v? V is x minus x0. This is small equal, you forget about that, f of x minus f of x0, and that's actually the subgradient inequality, and just written differently. So this shows p is in fact a subgradient at x0. So that was actually quick. Sorry, wrong focus of him. Okay. So a few subgradient rules. So of course, so now we have a new notion of differentiable, subdifferentiable, and then for differentiables, for derivatives, we have a lot of calculus rules, right? The derivative of the sum is the sum of the derivatives. The derivative of the product has a rule, and scalings are simple to treat. So basically, calculating derivatives is really mechanically. For subgradients, some things are very simple, and some things are subtle and not so simple. And today we want to treat the simple things, and the non-simple things will be the next lecture tomorrow. And the things which are not simple are the sum rule, which is the most straightforward thing for derivatives. For subdifferentials, it's not straightforward. The sum rule does not change, but it has a quirk, so it's not really always holds as you expect. So, but first for the simple things. Proposition 9.6, what was 5? Actually, this proposition was 9.5, right? It was 9.5, and the example was 9.4, right? So the proposition, so f from Rg to R convex, and then we have three things you want to say. So if we have, so translation, if phi of x is f of x plus x0, then the subgradient of the translation is just the subgradient at the translated point. Nothing bad happens here, so it's pretty obvious. If you translate the graph, you can translate all supporting hyperplanes, and also by formula it's totally straightforward to show. It's just doing basically nothing. So but what is now with scaling inside? Yep. Then the subgradient of the scaled function is kind of the scaled of the subgradient. So it also pulls out here. It's the same as for standard functions. For the standard derivative, for standard derivative. And the third one is, that's even simpler, if phi of x is just scaled from the outside, and here you need lambda non-negative for this to work, and then this gives you that the subgradient, it's just the scaled subgradient. That's totally straightforward. So, and all of this is standard direct consequences of the definition, so just writing down what that means to be in here, and you see that it's actually the same thing. So it's really, really straightforward. Okay. It was already page 5. Okay, so actually I have this example twice, but anyway, okay. Good. So I don't prove this. If you should just try to do it by yourself, and if you get stuck, maybe you just ask and chat. It's actually straightforward, writing down the definition, and then that's it. So now a little bit deeper result, but also not too, actually not too surprising. But so the subgradient is also able to calculate to characterize differentiability, and this is our proposition 9.7, and this says if f CVX, then it holds f is differentiable at x0 if and only if f is continuous at x0 and that the subdifferentiable only has one element. So if a function is differentiable at some, a convex function is differentiable at some point, if and only if it's continuous at that point and the subdifferentiable has exactly one element. Okay. And in this case, it holds that the gradient of f of x0 is exactly the subgradient of f of x0 is the set which just contains the gradient. So this direction is obvious. We already did that already, but this direction is the clue here, right? If you have that the subgradient is only one element, so there's only one subgradient, the subdifferentiable only contains one element, there's only one subgradient, then this implies differentiability. So the proof is like this direction. You already seen that, and now talk about this direction. Okay, the first step is to, without loss of generality, so WLOG, we take x0 to 0 and denote the subdifferential at 0, the element in there by W. Okay, so this just helps us to save a little bit of writing. And what we do is we define a helper function which is capital F, and we use v kind of as a direction as f of t times v for t a real number. So basically what we do is we, from the point 0, which is our x0 here, we look into the direction v. V is fixed, so we scale linearly by t's, and this is a real valued function. So this is kind of the function f look from 0 to look in direction v and how it behaves in this direction. So what we now do is, what is the subgradient of that function fv at 0? And it's simple to write down, and it's simple to check that it's exactly the inner product of v times w. And to see that, just write down the subgradient inequality for this guy here. What do you need here? And then you see that this is only, it has to be subgradients. So subgradients of this all have to be inner products with v of subgradient and subgradients of function f. Okay. And it's similar to the proposition 962. It's basically the same rule of calculus here. And so that means, again, by subgradient inequality, written slightly different, that 0 is larger or equal to fv at t minus fv at 0 divided by t minus w times v. So multiplying by t and rearranging gives you the subgradient inequality for fv in 0. And of course only this only holds for positive t, because for negative t we would have to flip the sign. So that's one thing. On the other hand, for positive epsilon, there exists a t epsilon such that you have that fv of t epsilon is smaller than fv fv of 0 plus t epsilon w times v plus t epsilon times epsilon. So, and why is that? At some point we have to use that the subgradient only has one element, and what what kind of this here means, this is true since the value w times v plus epsilon is not a subgradient of fv at 0. Okay, so this is an important step where we use that the subgradient only contains exactly this one element. So if you just add epsilon to it, it's not a subgradient anymore, means that the subgradient inequality cannot always hold. So there has to be some t epsilon for which this is not fulfilled, and this means the inequality goes in the wrong direction, like this here. Okay, now convexity, f of v is still convex. And this implies that f v of t is smaller or equal. So again, we write t as a slightly awkward linear combination of t epsilon and 0. I omit that one step here, but you'll see in afterwards where it came from. So t over t epsilon times f v of t epsilon plus t epsilon minus t over t epsilon f v of 0. So if you kind of do inverse convex combination here downwards, at that point you will end up exactly by this. So this is convex, these sum up to 1, and you see where this goes. Okay, and now we can use this inequality we have here. Is it, no, is it that? Yep, and see this is smaller equal to f of 0 plus t times v in the product with a w plus t epsilon, and we can rearrange that to f v of t minus f of 0 divided by t minus w times v is smaller equal to 1. Okay, and from here we already have the lower bound, right? This lower bound we already seen there, and so now we see if we let epsilon go to 0, you see that these so this holds for all epsilon, which means that and then there exists some t. Probably I was too quick here. So this is not true for all t epsilon. It's true for all t epsilon, which is between 0 and t epsilon. 0 and so this holds for all t, such that t is in the interval from t between to t epsilon. So this t here is not arbitrary. It cannot hold for all t, but it holds for all t which are like that. But if you now let t epsilon go to 0, then this t has to do something, and it has to go to 0 actually. So now this holds for all epsilon, which means this guy has to be 0 in the middle, and exactly this only can happen if this happens, that this limit here is actually equal to v times w, and this shows that our small f is differentiable with derivative at 0 equal to w by standard calculus. Okay. Yeah, and the clue is that the lower inequality you get for free, but for the upper inequality you have to use it if you add something to the one subgradient you have. It's not a subgradient anymore, which gives you the inequality in the other direction. Okay, and so now last but not least, one or two more examples. So actually the one example we had before just graphically, it comes now another time with a little bit of calculation First example is again the absolute value, and then it's in one dimension. You can calculate the subgradient completely by the different by the directional derivatives. So you only need to know the directional derivatives of f in direction 1 and in direction -1. So this is all you need to characterize the subgradient in this case, because this is an exact upper bound for the subgradient, and this is exact lower bound. So so the interval from this to this is always the full subgradient. In case they're equal, it's only 1. So it actually holds that this is the interval from the directional derivative from the left and the directional derivative from the right. And as you've seen, it's actually true. It's either -1, the interval from -1 to 1, or it's 1 for negative x, x0, x positive. Okay, good. And now for an example where the subgradient may not exist. How can that be? So how can it be that there's not a single hyperplane supporting the graph and touching it at this point? In the domain. So one thing where subgradient does not exist is, for example, again, consider an indicator function, but in a way that is maybe like that. So then at this point, again, you have a lot of subgradients as we had before. But at that point, of course, we have supporting hyperplanes, but they do not touch and the point here, because the point is not there. So the function value is plus infinity. So at this point, there's actually no subgradient. But it's also not a problem. It's also by definition, because this point here is not in the domain. So when for points not in the domain, it does not, why should there be a subgradient at that time? Yeah, but there's a different situation, and the different situation is if the function is kind of too steep. So the convex function may arrive at some point from below in a way that it does not hit plus infinity, but it's still infinitely steep. And the way we do it here is like that. So consider a function which looks like this, like the minus the square root, for example. And the function gets infinitely steep at that point, but it's still finite over here. And we do it like that. You consider this function. So the function we want to consider is plus infinity for negative x and minus the square root for x between 0 and 1, and here also for x larger than 1. So that would be the graph of the function here. And this is the epigraph here. So the epigraph is closed. Okay, so then of course subgradient at x is, for example, it's of course the empty set if x is negative or x is larger equal to 1, because it's not in the domain. It is here between 0 and 1, so if x is like this, like that, then it's differentiable at that point. So there's only one element, and there's just the derivative. The derivative is minus 1 over 2 square root of x. Just the ordinary derivative, nothing fancy to do here. What at the point x, point 1, x equals 1, what do you have here? Yeah, then it's the directional derivative from the left. It's like that guy. And from the right, you can get arbitrarily steep. So it has to be a closed interval, and the smallest number in that interval is the directional derivative from the left, which is exactly the value of the direction of the derivative evaluated at the point x, and this is kind of minus 1/2, and it of course has to be closed. But then it gets infinitely steep, and it's going to plus infinity. So this is this. And so what about the point x equals 0? That's the only point which is still missing. So what slope or what linear function can we put below the graph at that point? No, none at all. There's no function, so any linear function has to be infinitely steep. So it has to touch here, the linear function has to go to the origin, but any finite slope will not be totally below the function. So it's actually like this here. So that x equals 0 is in the domain of f. Of course, f of 0 is 0 and not infinity, but 0 is not in the domain of the subgradient. So you have a function where you may have a finite value at some point, convex function, but still no subgradient. Okay, and what we're going to show in the next lecture is that this cannot happen if you're in the interior of the domain. In the interior of the domain, you always have subgradients. So that's also a good thing. So in general, subgradients always exist in some way, at least in the interior of the domain. And if you don't have an interior of the domain, then it's getting a little bit more complicated, and functions like this are still interesting. And one have to think a little bit more about that situation. Okay, and also next time we're going to deal with the rules for the sum of subgradients. And there's a subtlety, so you can start thinking about it. What happens if you add two functions and have two subgradients at the same point for the both functions? Is the sum of these two subgradients still a subgradient or not, and the other way around? If you have a subgradient for the sum, can you decompose it into two subgradients of the individual functions? And it's not straightforward, actually. Okay, no answers for the questions. Yeah, you may just answer at a later point, and I'll just chime in when I've seen a few answers, and then say what it is. Okay, so anyway, in case nobody's using these questions anymore for learning, then I just may stop providing them, because why should I? So if you don't think that they're not useful, maybe I can come up with something else. Okay, that's it for today. Not was a lot of stuff and pretty fast, but anyway, you can also set pause if it's too fast for you. Okay, that's it for today, and we're going to see tomorrow and talking about subgradient calculus a little bit more.